To understand this, we must analyze the engineering that is typically hidden from view. Consider the most common seam in modern apparel, the standard overlock or surged seam. Visually, it is a web of threads looped over the raw edges of the fabric. Its primary function is to prevent fraying, and its execution is brutally efficient, making it the backbone of fast fashion. However, its speed comes at a significant cost to durability. The interlocking loops are vulnerable. If one key thread breaks, the entire seam can systematically unravel. Now, contrast this with a method built not for speed, but for permanence, the flat felled seam. This is not merely a seam, it is an architectural principle applied to textiles. Visually, it is clean, flat, and identified by two parallel lines of disciplined stitching. Here, the raw fabric edges are not just covered, they are enclosed, folded into one another, and secured with a double lock stitch. This creates a synergy where the fabric panels themselves become an integrated part of the seam's structure. There are no exposed edges and no single point of failure. It is an exercise in structural redundancy. This is why you find flat-felled seams on garments subjected to the highest levels of stress: premium denim, military-grade outerwear, and aeronautical textiles. The difference in longevity is not incremental, it is exponential. One is designed for disposability, the other is engineered for endurance. But the seam's architecture is only half of the equation. The structural integrity is equally dependent on two critical, often invisible components: the thread itself and its application density. A seam is only as strong as the thread that holds it together. An evolution in material science has moved us beyond generic cotton or polyester. Consider a thread spun from Tencel TM lyocell fibers. This is not just a filament, it is engineered for superior tensile strength and a uniquely smooth surface. This smoothness reduces friction against the fabric with every movement, minimizing the microscopic wear that leads to long-term failure. Choosing an optimized thread is a foundational decision for extending a product's life cycle. This brings us to the final, critical metric: stitches per inch, or SPI. A low SPI, common in mass-produced goods, might be anywhere from 6 to 8 stitches per inch. This creates longer, weaker points of connection that place isolated stress on the fabric. A high SPI, typically 12 to 15 or more, creates a dense, powerful bond that distributes force evenly across the seam. The visual difference is subtle, but the functional impact is absolute. It determines whether a garment is a fleeting purchase or a long-term asset. Ultimately, the narrative of a garment's quality is not written in its material alone. It is written in the invisible engineering of its construction. The choice between an overlock and a flat-felled seam, the selection of an advanced Tencel TM thread, and the precise calculation of stitches per inch, these are the details that define true lasting value. Genuine luxury is not found in the superficial feel of a fabric. It is embedded in the science and synergy of its construction. It is, and always will be, a function of superior engineering,